All right, hello everyone. In this video, I would like to talk about a new feature that we recently added in SCADEX, or rather a new improvement, and it's the split of the global idle CPU mask into multiple per NUMA node CPU masks. It's both a feature and an improvement. Well, the split is an improvement, of course, for large systems where you have like multiple NUMA nodes, for example, because in this way, having multiple per node CPU masks, so you can reduce the caching pressure like on the global CPU mask and ideally get better performance. I don't want to go through all the details of this patch set because it's quite big. I want to focus at the feature that we introduced, and there's new APIs that you can use in the BPF scheduler to implement some NUMA awareness concepts. For example, this one, for example, you can get, I don't know, from a CPU, you can get the corresponding NUMA node, or you can get the CPU mask, the idle CPU mask specific for a single node, or for example, pick an idle CPU within a specific NUMA node, stuff like that. And so that's the kernel part. At the time of the video, so this was targeting 6.15, and at the time of this video, 6.15 RC1 is out. So you should be already able to use that if you are using a recent kernel. But in terms of schedulers, I used this functionality in BPFland. BPFland is a SCADEX scheduler. It's written in C and Rust at the same time, and most of the logic is in BPF. Specifically, this NUMA awareness is pretty much all implemented in C and BPF. And yeah, that's the commit. Again, I don't want to go into details of this whole logic, but it's basically using the NUMA awareness APIs to pick an ideal idle CPU, knowing about the topology, the NUMA topology of the machine. So that can be beneficial for like large servers, for example. And I also implemented a NUMA node load balancer. So if the system is like becomes unbalanced, like the load on a specific node is bigger than the others, stuff like that. If there's an imbalance, it will try to compensate and do migrations when it's needed, like, because you don't want to migrate too much across different NUMA nodes, because that's an expensive migration, while at the same time you may want to migrate within the same node because you can distribute the load among all the available CPUs inside a node, and migrations usually within a node are cheap, so you definitely want to do that. Now, in order to do that, I'm going to simulate a complex NUMA system to see how the scheduler is performing. And to do that, I'm using virtmeng that, you can specify multiple parameters. In this case, I'm simulating a system with 16 CPUs, 4 sockets, 2 cores per socket, and 2 threads per core. And each socket has a separate NUMA node, so that we have 4 NUMA nodes. But here's the interesting part. The distance between one node and another is also non-uniform, like it's different. For example, going from, if you migrate a task from node 0 to node 1, there's a cost of 51. If you migrate a task from node 0 to node 2, the cost would be 31. So it's better to migrate to node 2 in this case. Node 0 to node 3 is 41, and so on and so on. So there's different costs. And if we want to show the topology, that's the topology, where we have the 4 NUMA nodes here, that this 4 blocks, green blocks, and there's an L3 cache within each block, and inside each NUMA node we have 4 CPUs and 2 SMT cores. Each one has 2 CPUs, of course. So with SMT, what's the deal with SMT in terms of scheduling? You don't want to, like, if there are physical cores idle, you don't want to pack tasks on the same physical core. Like if we have 2 tasks running on the same, in 2 CPUs of the same physical core, that's bad in terms of performance, because like SMT cores the sibling inside the SMT cores, they share execution unit, and they share components. And so, the two tasks that are running, they need to compete for these components. This works, for example, if you have a compute-intensive task or a memory-intensive task running at the same time within the same SMT core, because potentially they can use separate components. Like one is using more the execution units, the other is using more the load store units. But in general, like if you don't know the nature of the task, it's better to distribute tasks among the different SMT cores. So let's say in node 0, for example, if we have two tasks running, I would rather distribute the two tasks on the CPU 0 and CPU 2 rather than CPU 0 and CPU 1. At the same time, I don't want to be too aggressive at finding full idle SMT cores, because we have NUMA here as well. So I don't want to constantly bounce across different nodes, because that's expensive. So that's the topology that is simulated. And you can understand, like from a scheduling perspective, this is a very non-trivial scheduling problem, because we have topology complexity to take into account. It's not just the scheduling algorithm, it's also, the CPU allocation, let's say, or the distribution of tasks among the available CPUs. And there's, caches, NUMA, SMT, a lot of stuff to take into account. So let's simulate this topology using virtmeng. So now I'm inside virtmeng, and I'm running a SCADX kernel. Let's see first how the default scheduler is performing in this scenario. And I'm gonna start htop so that we can see like the load across all the CPUs. And if you do NUMA-ctl-h, we can see the NUMA table with all the different costs. So, for example, how do we read this? For example, if we are on node 0, that's the migration cost of a task. If I want to go on a different node, let's say I go from node 0 to node 1, there's a cost of 51. If I go from node 0 to node 2, there's a cost of 31. Node 3, there's a cost of 41. So if I'm node 0, I would very much like to migrate on node 2, because it's cheaper than migrating to node 1, for example. The same applies, like a similar concept applies to the other nodes, of course. All right, and in terms of CPUs, let's see how they're distributed. Actually, let's do this so we can see better. All right, CPUs, we have 2 by 2, like so 0, 1 is part of the same SMT core, 2, 3 is part of the same SMT core, and then 4, 5, 6, 7, that's 4, 5, 6, 7, 8, 9, 10, so 2 by 2, it's part of the same SMT core. And 4 by 4, it's like, that's the NUMA node 0, NUMA node 1, NUMA node 2, and last, NUMA node 3. So that's how the topology works. So if we see like something running around here is going to be 0, 3, is going to be node 0. If it's something is running in 8, 11, it's node 2. Okay, I hope that's clear. Let me open also a NUMA-ctl here so we can keep track, like if we see migrations, we can keep track of how expensive was the migration. And so right now we're running the default Linux scheduler. And what I want to do, like to simulate a workload, is to run a spinner. This task is just spinning on a CPU, and it's printing in which CPU is running every second. That's very simple, nothing special here, but it's useful to like keep track of the migrations. Now, what I'm going to do in this other session is to, stress the spinner task with other CPU intensive tasks, but I'm going to set the affinity of this compute intensive task in certain CPUs where I want to see how the scheduler reacts by doing that. So for example, if I start another CPU intensive task on CPU 0, I'm on CPU 1, right? If I start another task on CPU 0, I would expect that the scheduler would migrate the task on a different CPU because I don't want to use the same SMT core. So let's see what happens. Yeah, so in this case, the scheduler decided to keep both tasks running on the same physical core. Can be good in terms of caching, but in this case, I mean, they don't share cache, so it's bad for that. It's also bad in terms of like pure CPU performance because I'm sharing the same execution unit. So I was expecting that the scheduler would migrate the task. But anyway, let's force a migration by starting another CPU intensive task on the same on CPU 1 that is the same CPU that the spinner is using. And we should be able to see a migration. Okay, we even jumped on a different node. Now from node 0 we went to node 2. That's good actually, because we can see here the cost from going to node 0 to node 2. Node 2 was the best pick. Like, yes, that was a reasonable migration. Now if I start another task on CPU 8, what happens? Yeah, you see we're still using the same physical SMT core. I don't like that. So I don't know, let's do 9. It migrates to 10, or maybe 11, not 10. Let's do the same trick starting on 11. So I'm starting to fill all the nodes, with load. Oh, where do we, oh, now we jumped back into node 0 because I was overloading the node 2. Was that a good decision? Let's see. So I was on node 2 and we jump back on node 0. Well, that was a poor decision because from node 2, you see the cost is 31. It would have been a better decision to move to node 3. Moreover, node 0 was already overloaded. So, I mean, this decision doesn't make much sense because yeah, at least, well, we jumped on a full idle SMT core and not on a partial idle core. So, you know, there are some inefficiencies here. At least we're not constantly bouncing among different nodes, which is good. There's, you know, some kind of soft affinity logic in the default scheduler, which is reasonable. The first migration was reasonable from node 0 to node 2, despite the fact that we're still using partially idle SMT cores, which was not ideal. But anyway, you know, let's kill everything, and we start from scratch now. But now we're using BPFLAN, and we see like, okay, now the BPFLAN scheduler is running. I go back to the same session. We start the spinner again, and we see what happens. So I started on node 0, fine. Let's do the same trick, you know, of stressing the node. We can see like more migrations now already, and that's because every time that I type something on the keyboard, I'm still using node 0, so I'm competing with the CPUs on node 0. And if BPFLAN inside a node is very aggressive at finding full idle SMT cores, so you see like if there's a task that is occupying a CPU, BPFLAN prefers to do a migration within the same node on a different full idle SMT core because it, you know, better isolation and better performance isolation. Now, for example, I'm on CPU 2. If I start another CPU intensive task on CPU 3, I will trigger a migration for sure. Let's see. And yes, in fact, now you see that's a better distribution because I'm using CPU 1 and CPU 3, which are both in the same node 0, but they both use full idle SMT cores. So these two tasks are now performing much better. They're running both of them on the same core. Now, they're still in balance across the NUMA nodes, but that's fine. I only have 2 tasks. Like this node is only used at 50%, so the load balancer doesn't kick in. However, so now I'm on CPU 1, right? Let's start another compute intensive task on CPU 0, and I should have a migration. Exactly. We migrated to node 2, which is a good decision, I think, because we were on node 0 and node 2 is the cheapest one. So that was good. We're still using a full idle SMT core, which is fine. So no, we should be able to get the same performance isolation. We had a NUMA migration, but that was making sense because we were like overloading at node 0 and everything, like all the other nodes were completely idle. So why to keep everything packed on the same node? I mean, it was a reasonable decision to migrate. Now, I'm going to stress the SMT core where I'm running right now, which is, CPU 8 and 9. So I start a CPU intensive task on CPU 8. And what happens? Boom, I have another migration. So there's a migration, but still within the same node. Now, let's do, again, starting another CPU intensive task on CPU 10 to force another migration and, annoy this spinner task that is running. And now, boom, I bounced on node 3, which is that a good decision? Let's see. I was running on node 2. That's the line. So an option would have been to go to node 0, but that was expensive. You see the cost would be 31. And by the way, node 0 is currently quite busy. I mean, there's not a full idle SMT core. So where do I go? Node 1 is fully idle, but the cost was 21. Node 3, however, was also fully idle with a cost of 11, which is less than 21. So the ideal decision was to pick a fully idle SMT core inside node 3. And now I'm running in node 3. Let's stress this spinner task even more by starting, occupying the SMT sibling CPU, that is 12. And yes, I'm occupying CPU 12. I was running on 13. And now what? Okay, I migrated. I migrated because probably this node was also busy because I pressed something on the keyboard and I bounced from node 3 to node 1. Was that a good decision? If we see here, like that was very expensive. So not a good decision. But there's also the fact that node 0 was busy, node 1 was idle, node 2 was busy, node 3 was busy. Everything was busy except node 1. So despite the higher cost, this NUMA node was fully idle. So yeah, I mean, we can afford an expensive migration if we go on a node that is completely idle. We may get a little performance drop to do the migration, but once we are there, we have a node completely available for us. So all in all, that seems a better scheduling what BPFLAN did compared to the default scheduler. And this is just an example to show what you can do with SCADAX. You can easily apply these logics in your BPF scheduler, or you can use BPFLAN and with some tweaking here and there. And if you have a complex topology, like if you want to apply the same logic to L3 caches, for example, or if you have hybrid cores and you want to do something similar, then you can craft your own scheduler simply using the new APIs. So yeah, that's all for now. I hope you enjoyed the video. If you have more questions about BPFLAN or SCADAX in general, feel free to comment down below and I'll be happy to help. Okay, bye everyone.